A single stone block can weigh more than 10 elephants. Ancient civilizations moved these giants across continents without engines or steel. This video will give you the definitive explanation for how these impossible journeys were made. How did stones from distant mountains find their way into the heart of a pyramid? What secret allowed statues to walk across an island? The answer lies in a lost art of engineering that turned simple physics into monumental power. What do you think is the ultimate limit of human collaboration? 70 tons is not just a number. It is a physical reality that presses down with the force of a fully loaded semi-truck concentrated into a single slab of rock. To move such a block 500 miles across a landscape of hills, rivers, and soft earth is a logistical puzzle that would give a modern engineer pause. Yet this was the everyday challenge for the architects of our ancient world. Let us break down exactly why this task borders on the impossible. First, there is friction. A stone of that mass resting on the ground creates an immense bond with the earth. Simply to get it to budge requires overcoming a force that can be equivalent to the combined pulling strength of hundreds of people. Then there is ground pressure. Place that stone on soft soil or sand, and it will sink, creating its own trench and becoming hopelessly stuck. Every single step of the journey had to be managed, a delicate dance with physics using only the materials nature provided: wood, fiber, and human ingenuity. The builders of Stonehenge sourced their iconic bluestones from mountains over 150 miles away in Wales. The Egyptian pyramids incorporated granite from quarries more than 500 miles up the Nile. And on a remote Pacific island, the creators of the Moai carved statues weighing up to 80 tons, then moved them miles from the quarry to their coastal platforms. Each of these projects faced a unique constellation of obstacles: dense forests, desert sands, and volcanic rock. But they all shared this same fundamental confrontation with scale. To appreciate the elegance of their solutions, we must first stand in awe of the sheer weight of the problem. This was not merely construction, it was a conversation with the earth itself, a negotiation of forces where every victory was hard-won. The solution began with a simple, powerful image: the unified rhythm of a team hauling on ropes. This was the sledge and roller system, a foundational technology that turned dragging into a precise science. Picture a massive wooden sled, a platform crafted from sturdy timbers with a stone block securely lashed on top. Teams of workers would pull on ropes attached to the front, but the true innovation lay beneath their feet, on the ground itself. The path was not left to chance. Ancient engineers would prepare a track, often smoothing the earth and then applying a lubricant. Water was a common choice, poured onto the soil to create a slick, muddy surface. In other cases, they might use wet clay or even animal fats. This layer of lubrication was transformative. It reduced the friction between the wooden sledge runners and the ground so dramatically that the force required to pull the load could be cut by half or more. Experimental archaeology has shown that on a properly prepared, lubricated track, a team of just 20 people could move a stone weighing several tons with a steady, controlled effort. But the innovation did not stop there. To prevent the sledge from digging into the soft, wet track, workers would place a series of cylindrical logs, rollers, perpendicular to the direction of travel. As the sledge was pulled forward, it would roll over these logs. The rollers acted as temporary, moving sections of road, distributing the immense weight and preventing the structure from bogging down. As the sledge passed over a roller, workers behind would rush to pick up the now freed log and run it to the front, creating a continuous cycle of motion. It was a system of beautiful, repetitive logic, a conveyor belt made of wood and human coordination. This method was almost certainly used across the ancient world, from the flat plains surrounding the pyramids to the forest paths leading to Stonehenge. It transformed an impossible drag into a manageable, rhythmic procession, setting the stage for even more sophisticated engineering to come. Rhythm was the secret. The steady pull of ropes gave way to a different cadence, the measured thump of wood on wood, and the coordinated shouts of a team working in perfect unison. This was the leverage and pivot technique, a method of astonishing precision that turned a stone colossus into a carefully balanced instrument. Think not of dragging, but of coaxing, of convincing a mountain to take a series of tiny, deliberate steps. Teams would insert long, sturdy wooden poles, often of oak or another strong timber, beneath one edge of the stone slab. Using a smaller rock or a prepared wooden block as a fulcrum, they would apply their collective weight to the opposite end of the pole. The principle of mechanical advantage did the rest, a small force exerted over the long lever arm generating enough upward power to lift a corner of the megalith just an inch or two off the ground. Once elevated, workers could quickly slide a flat stone or a bundle of wooden shims underneath. Then, as the lever was released, the block would settle onto this new, slightly higher support. The process was repeated, levering up the opposite side, adding another shim in a patient, rocking rhythm. With each cycle, the entire stone was incrementally raised onto a stable platform of packed supports. But how did they move it forward? The answer lies in a clever shift from lifting to nudging. Once the block was elevated and stable on its temporary cribbing, levers could be inserted horizontally. By applying pressure against a fixed pivot stone placed strategically to the side, teams could tilt and then ever so slightly shift the mass laterally, inching it along its intended path. Ancient carvings and modern experimental reconstructions show this was a dance of micro-adjustments. A team might spend an entire day moving a stone just a few feet, but those feet were gained with absolute control, without the risk of the stone sliding uncontrollably or sinking into the earth. This technique was indispensable for the final, delicate act of construction. Positioning an 80-ton lintel atop two upright stones at Stonehenge, or seating a massive statue perfectly onto its ceremonial platform, required more than raw power. It demanded the finesse of a master craftsman. The leverage and pivot method provided exactly that, a testament to an ancient understanding of physics that was both intuitively grasped and brilliantly applied. It reveals a mindset that saw the environment not as an obstacle, but as a toolkit where every rock and log held potential energy waiting to be unlocked. But perhaps the most elegant solutions involved no dragging or levering at all. For some of the heaviest stones, the journey was a quiet float down a liquid highway. The third method transforms our understanding of the landscape, where rivers and canals were not obstacles but the very means of transport. This is the world of aquatic engineering, where megaliths were turned into cargo and water did the heavy lifting. The most iconic example flows through the heart of ancient Egypt. The Nile River was more than a source of life. It was a dynamic, pre-built transport network running directly from the southern quarries to the pyramid construction sites near modern-day Cairo. Granite blocks weighing 50 tons or more were loaded onto enormous, purpose-built barges. These vessels were feats of woodworking and buoyancy calculation, designed to be stable under phenomenal loads. Historians and archaeologists studying tomb paintings and logistical records suggest a process where stones were quarried during the dry season. When the annual Nile flood arrived, raising water levels and connecting channels that were otherwise dry, these loaded barges were set adrift. The current would carry them northward with the flow, a journey of hundreds of miles where the only required propulsion was strategic guidance from smaller steering boats. The energy expenditure was minimal compared to overland hauling, a brilliant synchronization of human timing with the natural rhythm of the planet. This principle was not confined to Egypt. In other parts of the world, cultures may have manipulated water in different ways. Some researchers propose that the builders of Stonehenge used a combination of rivers and temporarily dug canals to bring the bluestones through the landscape of ancient Britain, reducing the overland haul to the final stretch. On islands, tidal flats could have been used, with rafts floated at high tide and settled onto prepared tracks as the water receded. The common thread is a profound reimagining of the environment. It was not about conquering the distance with brute force, but about reading the map in a different way, seeing the potential for movement in the reflective surface of a river. The engineering challenge shifts from overcoming friction to understanding buoyancy and stability. Building a raft that can support 80 tons without buckling or capsizing requires a deep, practical knowledge of materials and balance, a naval architecture born of necessity. This method speaks to a holistic vision where the stone's journey from quarry to monument was a single, fluid design, with water as the silent, powerful partner in the process. It reveals that the true monument was not just the final standing stone, but the entire, invisible network of thought and adaptation that brought it there. The earth itself became a tool reshaped by intention. To move a mountain, you sometimes have to build a new one first. This is the story of terrain modification, where the journey of a megalith was not a path found, but a path forged. The challenge shifted from simple transport to large-scale civil engineering, demanding a vision that integrated the stone's final destination with a permanently altered landscape. Imagine the process not as a single event, but as a months-long campaign that began long before the first rope was pulled. Teams of workers would clear forests, level uneven ground, and fill in gullies to create a smooth, stable roadway. In some cases, they built raised causeways of packed earth and stone, elevating the transport route above soft, marshy ground to prevent the sledge from sinking. These were not temporary trails, they were monumental works of infrastructure in their own right, the unseen foundations of the visible wonder. A profound example lies in the Bekaa Valley of Lebanon, home to the Roman temple complex of Baalbek. Here, the foundation stones, known as the trilithon, are among the largest ever moved by human hands, each weighing an estimated 800 tons. The quarry for these behemoths sits nearly a mile away. Researchers studying the site have identified what appears to be a meticulously prepared transport route. The ground between the quarry and the temple platform is not a random stretch of valley. It shows evidence of being leveled and reinforced, a roadbed built for a singular, unimaginably heavy purpose. The stone's journey was likely a continuous, engineered slope, a highway for giants. This approach reframes our entire understanding of these projects. It was not just about the physics of moving a block, it was about the logistics of transforming the world around it. Building a ramp to raise stones to the top of a growing pyramid is the most famous example of this principle, a temporary mountain of earth and brick that grew alongside the structure itself. But the concept applies everywhere. The famous stone rose at Karnak in France, or the long, processional avenues leading to ancient temples, all suggest that the builders thought in terms of systems, not just objects. The true scale of their achievement becomes clear only when we see the empty space around the monument, the cleared land, the graded road, the engineered ramp, not as a backdrop, but as the critical first phase of construction. The stone did not just arrive, it was ushered in along a processional way that was itself a testament to human will. This holistic planning reveals a mindset that saw no separation between the monument and the journey that created it, a complete reimagining of the very ground beneath their feet. The image of 1,000 oxen straining against ropes is a powerful one, but history is rarely so simple. The role of domesticated animals in moving megaliths sits in a curious space between undeniable potential and practical limitation. On paper, the physics are compelling. A team of oxen can generate a pulling force far exceeding that of a human crew. They are strong, they can be trained, and they represent a form of living machinery that many ancient cultures possessed. So why isn't every ancient monument surrounded by carvings of vast bovine teams? The answer lies in the messy reality of the task. Controlling a large team of powerful animals on a narrow, prepared track with a multi-ton stone in tow is an exercise in precision that borders on chaos. A single spooked animal could veer off course, tangling ropes and potentially causing a catastrophic shift in the load. Furthermore, the logistics are daunting. Each ox requires vast amounts of fodder and water, supplies that must be transported along with the stone itself, turning a difficult journey into a moving feast that could strip the landscape bare. On steep inclines or uneven, rocky ground, the risk of injury to the animal's hooves and legs was high, making them less reliable than human teams who could navigate more delicately. The evidence we have suggests animal power was likely used, but in a supporting, specialized role. In ancient Egypt, tomb paintings do show cattle being used to drag statues on sledges, but often in smaller numbers and on clearly prepared ceremonial grounds. For the long-distance haul of pyramid stones, the consistent Nile current was a far more dependable engine. In contexts like the rolling hills of Britain or the rugged terrain of Peru, human labor, with its superior coordination and ability to work in confined spaces using levers and pivots, may have simply been the more adaptable, controlled choice. The beast of burden was not a magic solution, but another tool in the kit, one weighed against its considerable cost and complexity. This shifts our perspective from a single, dramatic explanation to a more nuanced reality. The movement of these stones was a symphony of methods where animals might provide the initial pull on a flat plane, humans took over with levers for precise placement, and water carried the load across vast distances. It was a pragmatic calculus, always choosing the right force for the right phase of an impossible journey. The physics of levers and the flow of rivers provided the means, but they were nothing without the will to apply them. The true engine that moved mountains was not made of wood or stone, but of people, a vast and intricate social machine operating with a single purpose. To coordinate the journey of a single megalith required a symphony of human effort, sustained not for days but for seasons, sometimes for generations. This was an undertaking that reshaped entire communities, demanding an organizational genius that rivals the engineering itself. How do you feed 1,000 workers in a remote quarry? How do you maintain morale when the goal is a decade away? The answers lie in the invisible architecture of society that rose up to meet the stone. We often picture endless lines of conscripted laborers toiling under a whip, and while some projects undoubtedly relied on centralized authority and duty, the reality was far more nuanced and often more voluntary. In many cultures, these monumental works were deeply tied to communal identity and spiritual belief. Participating in the movement of a sacred stone could be an act of profound religious devotion, a way to earn honor for one's family or clan, or a necessary civic duty that bound the community together. The work was often seasonal, aligned with agricultural cycles. When the harvest was in and the fields lay fallow, the people turned their collective energy to the great project, transforming idle time into eternal legacy. This cyclical pattern made the endeavor sustainable, woven into the very rhythm of life rather than breaking it. Within this mass of people existed a precise hierarchy of skill. It was not a chaotic mob, but a structured organization with clear roles, much like a modern construction site. There were the pathfinders and surveyors who scouted and prepared the route in advance. There were master carpenters designing sledges and levers. Teams of rope makers produced miles of durable cordage from plant fibers. Cooks and water bearers formed a vital support network, while coordinators with signal flags or drums kept the pulling teams in perfect rhythm. This specialization was key. It meant that strength was directed by knowledge, that every push and pull was part of a calculated sequence. The command chain, from a chief engineer down to the newest worker, ensured that a single, shouted order could translate into the synchronized heave of 100 people. The scale of this social engine is humbling. To move the largest stones at Baalbek or the pyramids, researchers estimate that crews numbering in the many hundreds, perhaps even over 1,000, would have been mobilized just for the transport phase. Housing, feeding, and managing such a temporary city was a logistical feat equal to moving the stone itself. It required administrators, scribes to track supplies, and hunters or traders to secure provisions. This was not merely construction, it was the temporary creation of a new, purpose-driven society in the wilderness. The monument that finally stood was therefore more than an object. It was a testament to what that society could achieve when united by a common vision. The stone's final resting place marked not just the end of a physical journey, but the culmination of countless individual stories of effort, collaboration, and shared belief. In this light, the true wonder is not that the stone was moved, but that so many people chose to move it together, turning impossible weight into a collective act of meaning. All the theories in the world mean nothing if they fail in the dirt. Blueprints drawn on parchment are one thing, but the true test comes when sweat meets stone and rope bites into wood. This is the domain of experimental archaeology, a field that asks a simple, profound question: can we do it ourselves? Researchers abandon modern tools and conveniences, attempting to reconstruct ancient methods at full scale, using only the materials and knowledge available at the time. Their goal is not to prove a single idea, but to feel the problems and discover the solutions through direct, often grueling, experience. It transforms historical speculation into a physical conversation with the past. One of the most famous experiments took place on the remote slopes of Easter Island. For decades, the question of how the massive Moai statues were transported miles from the quarry haunted archaeologists. Oral traditions spoke of the statues walking, a poetic clue that sparked the walking theory. A team led by researchers Terry Hunt and Carl Lipo decided to test it physically. They fashioned a scaled-down concrete replica of a Moai weighing about 5 tons. Then, using 3 teams of ropes and a careful rocking motion, they demonstrated how the statue could be walked upright in a controlled sway, pivoting from side to side down a prepared path. The experiment was a revelation. It showed that a relatively small group, perhaps just 15 or 18 people, could move a multi-ton statue hundreds of feet in a day with a rhythmic, coordinated effort. The statue did not drag, it progressed with a dignified, almost living gait, giving literal meaning to the ancient stories. The data was invaluable, not just for the method's feasibility, but for its efficiency. It required far fewer people than anyone had previously assumed. On the other side of the world, another team tackled the mystery of Egyptian obelisks. These single pieces of granite, some weighing over 400 tons, were often transported by barge on the Nile. But how do you load such a monstrous stone onto a wooden ship without cranes? The historian and engineer Obayashi Corporation attempted a reconstruction based on a relief from an ancient temple. They built a canal next to the river, floated a barge into it, and then used a system of counterweights and levers to carefully tilt a massive stone replica onto the vessel. The experiment was a staggering success, proving the conceptual soundness of the method, but it also exposed hidden complexities. The team discovered the critical importance of the barge's buoyancy and the precise timing needed to prevent a catastrophic capsize. These are details no text would ever think to record, yet they were the difference between triumph and disaster for the ancient engineers. Each experiment like this adds a new layer of understanding. They move us from asking could they have done it this way to learning exactly how they must have done it, complete with all the improvisations, shouted commands, and moments of sudden insight that defined the original process. The stones themselves become teachers, and the past becomes something we can not just study, but physically reenact and for a moment truly touch. the Great Pyramid stands as the ultimate expression of ancient logistics. Its 2.3 million stone blocks, some weighing over 50 tons, represent a puzzle of movement on a scale that still defies belief. To understand this, we must follow a single granite block on its impossible journey, a 500-mile odyssey that began deep in the earth. Far to the south, in the quarries at Aswan, workers used simple tools and ingenious technique to free this colossal piece of the planet. They would drill a line of holes along the desired fracture line, insert dry wooden wedges, and then soak them with water. As the wood expanded with tremendous force, it would cleanly split the granite along a perfect plane. Once liberated, the block faced its first great challenge, getting to the river. It was likely loaded onto a heavy wooden sledge and pulled over a lubricated track of wet clay by teams of workers, inching down to the banks of the Nile. Here, the real magic of Egyptian engineering took over. The block was transferred onto a colossal, purpose-built barge. These vessels were marvels of their own, designed for a single, sacred cargo. A recent discovery at the Giza Plateau itself sheds stunning light on this phase. Archaeologists have uncovered the remains of a massive, man-made harbor basin right at the foot of the pyramid complex, connected by a now-vanished canal to a branch of the Nile. This was not a simple riverbank. It was a bustling, ancient port designed specifically to receive these floating mountains of stone. The block's journey north would have been timed with precision, waiting for the annual flood when the river was high and the currents favorable. For weeks, it would float silently northward, a passive passenger on the life-giving waters, until it reached the bustling harbor at Giza. Unloading a 50-ton block from a wooden boat required another act of brilliant engineering. Researchers suggest a system of counterweights and levers, or perhaps a carefully dug slipway that allowed the barge to be grounded and the stone slid onto a waiting sledge. Now came the final, most debated ascent, getting the block up onto the growing pyramid. The classic image is of a single, massive straight ramp stretching into the sky, but the material requirements for such a structure are almost as vast as the pyramid itself. More likely, the Egyptians used a clever, spiraling ramp that wrapped around the pyramid's rising sides, or a series of smaller, zigzagging ramps built from the abundant local Tafla clay and gypsum. As the pyramid grew, so did this temporary mountain of earth, a scaffold of soil that vanished once the capstone was set, leaving only the perfect geometric form behind. This case study reveals the true genius was not in one single trick, but in the seamless integration of many. Water transport handled the impossible distances, harbor engineering managed the transfer, and ramp systems conquered the vertical climb. It was a supply chain of monumental ambition where every phase from quarry to capstone was part of a single, fluid design. This logistical symphony, conducted over decades, turned the slow flow of a river and the patient work of thousands into a permanent echo in stone. The granite of Egypt speaks of imperial power and logistical might, but the blue stones of Stonehenge whisper a different kind of mystery. Nestled within the famous circle of giant sarsen stones are dozens of smaller, distinctive pillars of spotted dolerite, a rock that geology tells us could only have come from one place, the Preseli Hills in Western Wales. This source lies over 140 miles away, across a landscape of rolling hills, dense forests, and significant waterways. The question of how these 4-ton stones arrived on Salisbury Plain has sparked one of archaeology's most enduring debates, a clash between two fundamental forces, the immense, slow power of nature and the determined will of humanity. The first theory points to an ancient natural courier, the glaciers of the last ice age. Proponents of this idea suggest that massive ice sheets, which once covered much of Britain, could have plucked these blue stones from the Welsh mountains and carried them eastward as they advanced and retreated over millennia. According to this view, the stones were not transported by people at all, but conveniently deposited by nature relatively close to where Stonehenge would later be built, a kind of prehistoric quarrying service performed by the climate itself. The builders would have simply collected these erratics, these glacial travelers, from the surrounding countryside. It is an elegant, energy-saving explanation that credits chance with a starring role. Yet, significant problems arise with this glacial map. Detailed geological surveys have failed to find a scattering of similar Preseli bluestones anywhere on the plains east of Stonehenge, the trail of breadcrumbs one would expect from a melting glacier. Furthermore, the specific types of bluestones found at Stonehenge match very particular outcrops in the Preseli Hills, not a random sampling from a wide area. This points toward a deliberate selection, a conscious choice of stone from a sacred landscape, rather than a simple gathering of whatever was locally available. This leads us to the second, more human-centered theory, a journey of extraordinary intention. If glaciers did not do the work, then people must have. The proposed route is a masterpiece of mixed-mode transport, a testament to prehistoric ingenuity. After being quarried, the stones were likely dragged down to the nearby river Nevern or another watercourse. From there, they could have been loaded onto rafts or lashed between canoes to travel along the Welsh coast, a treacherous but possible voyage around the peninsula. They might then have navigated eastward via a network of rivers like the Avon and the Wailai, pushing deep into the heart of what is now England. Where the rivers ended, the overland haul began. This final leg would have been the most grueling, requiring teams to pull the stones on sledges across miles of terrain, possibly using the same lubricated track and roller systems we have discussed. This theory frames the bluestones not as cargo but as pilgrims. Their immense journey transforms them from simple rocks into powerful relics, their value multiplied by every mile traversed. Bringing a piece of a distant, holy mountain to the center of a new ceremonial complex would have imbued Stonehenge with a profound spiritual geography, connecting it to the power of far-off lands. The debate between glacier and raft is more than academic. It asks what we believe about our ancestors. Was their greatest monument partly a gift of geological chance, or was it entirely a product of cultural will, a deliberate act of connection over a seemingly impossible distance? The weight of evidence now leans heavily toward the human story. The precision of the stone sources, the lack of a glacial trail, and the sheer symbolic power of such a journey suggest a people not limited by their landscape, but motivated by it, willing to move mountains, or at least very large stones, to fulfill a vision that resonated across generations. The bluestones stand as quiet, enduring proof that some distances are measured not in miles but in meaning. A world away from the river highways of Egypt, a different kind of mystery stands in silent rows. On the most isolated inhabited island on Earth, a place called Rapa Nui, the giant stone faces known as the Moai gaze inland from their coastal platforms. Their creation is a marvel, but the journey they took is the true wonder. Carved from the volcanic rock of an inland quarry, hundreds of these statues, some taller than a 4-story building and weighing as much as 2 blue whales, were somehow transported miles across a rugged, rolling landscape to their final resting places. With no large trees for rollers, no rivers for barges, and no beasts of burden, the islanders faced a uniquely constrained puzzle. Their solution may be the most elegant and intuitive of all, a method so simple it was hiding in plain sight within their own oral history. For generations, stories passed down spoke of the Moai walking to their platforms, guided by the spiritual power of chiefs. For a long time, this was dismissed as pure myth, a poetic metaphor. But what if it was a literal, technical description? This is the heart of the walking theory, an idea that transforms a spiritual story into a practical manual. The concept is breathtaking in its directness. Imagine a statue standing upright, not lying flat on a sledge. Ropes are tied around its head and base. 3 teams of workers take positions, one on each side to control the sway, and one behind to provide stabilizing counterweight. With coordinated pulls, the teams would rock the statue forward, pivoting it on one corner of its base, then the other. Each controlled rock would tip the center of gravity just enough to produce a small forward shuffle. The statue would not be dragged. It would progress with a slow, dignified, side-to-side gait, literally walking down a prepared path. This method leverages the statue's own immense weight and vertical orientation, using physics to convert a rocking motion into forward momentum. It requires relatively few people, perhaps just 15 to 20 for a medium-sized Moai, but it demands absolute coordination and rhythm, a shared heartbeat between the pullers. The theory moved from compelling idea to plausible reality through hands-on experimentation. Researchers, working with members of the local community, fashioned a concrete replica of a Moai weighing about 5 tons. Using only ropes and the walking technique, they successfully moved the statue hundreds of feet in a matter of minutes. The experiment was a revelation, not just for its success, but for its efficiency. It required no complex infrastructure, no vast consumption of resources, just human ingenuity applied to the geometry of the statue itself. It proved that the islanders' ancestors could have achieved this feat with the materials and knowledge they possessed, turning their oral tradition into a demonstrable engineering principle. This case study speaks volumes about human adaptation. On an island with finite resources, where every piece of wood and fiber was precious, the most brilliant solution was also the most economical. It did not fight against the environment, but worked in harmony with it, using the statue's form as the primary tool. The journey of the Moai becomes a powerful metaphor for innovation born from limitation. It shows us that the answers to our greatest challenges are not always about adding more, but about understanding more deeply what we already have. The silent walk of the giants across Rapa Nui stands as a timeless lesson that sometimes to move a mountain, you simply need to learn its rhythm. Getting the stone to the site was a monumental achievement, but the real test of genius began when it stopped moving. The final act of construction demanded a different kind of magic, one of millimeter precision and breathtaking control. How do you lift a stone taller than a house and set it perfectly vertical? How do you lower a 50-ton lintel onto 2 upright pillars with the accuracy of a master watchmaker? This phase required physics to become an art form. One of the most reliable methods for raising a standing stone involved a partnership with the earth itself. Workers would dig a V-shaped trench, sloped on one end, and carefully guide the stone down into it so that its base rested at the bottom of the V and its top leaned against the far wall of the pit. This leaning position was stable, a temporary rest. Then the slow, meticulous work of backfilling began. Using ropes to control the stone's tilt, teams would gradually pack earth and stones back into the trench under the raised base. With each basket of material added, the stone's center of gravity would shift infinitesimally upward, causing it to pivot toward vertical. It was a patient, controlled dialogue with gravity, where the earth that had been removed to receive the stone now became the tool to lift it. The process could take days, with constant checking of alignment using simple plumb lines made of cord and stone. For even heavier stones or for placing horizontal lintels, a different system came into play: the frame and counterweight. Imagine a massive wooden tripod or a frame erected over the intended placement site. From its apex, a strong rope would be threaded through a series of guide stakes and attached to the stone waiting on the ground. On the opposite side of the frame, a large basket or container would be suspended. This basket was the counterweight. Workers would slowly fill it with rocks, earth, or even water. As the counterweight descended with increasing mass, it would pull on the rope, hoisting the stone with a smooth, mechanical advantage into the air. This method allowed for incredible control. The lift could be stopped, adjusted, and fine-tuned simply by adding or removing material from the basket. Once the stone was suspended at the correct height, teams on the ground could use levers to nudge it laterally, sliding it the final few inches onto its waiting supports. The sophistication of these techniques reveals a critical truth. The transport and the placement were not separate projects. They were two movements in a single symphony of planning. The prepared roadway for the sledge often led directly to the construction ramp. The orientation of the trench for raising a stone was calculated from the moment it was quarried, its future alignment already decided. This integration is what makes sites like Stonehenge or the Great Pyramid so astonishing. The stones were not just placed, they were positioned with celestial precision. The heel stone at Stonehenge, for example, frames the sunrise on the summer solstice because the entire process, from quarry to final setting, was guided by astronomical observation. The architectural plan and the logistical plan were one and the same. This final act of setting the stone was therefore the quiet culmination of years, sometimes generations, of coordinated thought. It transformed raw, transported mass into defined, meaningful space. The moment the last supporting lever was removed and the stone stood or rested under its own perfect balance, the impossible journey was complete. The weight was no longer a problem to be solved, but a monument to the solution. The true strength of an ancient rope was not in its individual fibers, but in the collective twist that bound them together. This principle of synergy defined every tool used to move megaliths, where the limitations of natural materials were not weaknesses to be overcome, but design parameters to be mastered. The ropes that hauled 50-ton stones were not thick, crude cords, but sophisticated products of applied botany and physics. In Egypt, the favored material was the fiber from the date palm or the hafa grass, plants that were abundant along the Nile. Workers would painstakingly harvest these long, tough strands, then twist them together into yarns. Multiple yarns would then be twisted in the opposite direction to form a strong, balanced strand, and several of these strands would be plaited or laid together to create the final rope. This counter-twisting technique is crucial. It locks the fibers together, distributing any pulling force evenly across the entire cross-section and preventing sudden, catastrophic unraveling. A rope made this way, even from humble grass, could have a tensile strength comparable to some modern synthetic cords, capable of withstanding the immense, sustained tension of a team hauling a sledge up a ramp. The choice of material was always local and logical. In Northern Europe, builders likely used lime bark or willow, materials both flexible and strong. On Easter Island, the answer came from the hau-hau tree, whose inner bark produced a famously durable cordage. Each culture identified and optimized the strongest fiber their environment provided, turning plants into power cables. The sledges and rollers that carried the weight were a study in wood selection. Not just any tree would do. The ideal timber needed a combination of properties: strength to resist cracking under immense pressure, and a natural lubricity to slide smoothly over a prepared track. In many regions, oak was a premier choice for sledges. Its dense, interlocking grain structure gave it tremendous compressive strength, allowing it to bear tons of weight without deforming. For the rollers placed underneath, a slightly softer wood like cedar or elm might be preferred. These woods were still strong, but their more open grain could better absorb the repeated impact and crushing force without splintering apart. The very shape of the roller was an innovation in force distribution. A cylindrical log spreads the sledge's weight along a line, rather than concentrating it on a single point, dramatically reducing ground pressure and preventing the whole assembly from sinking into soft earth. The builders understood wood as a living material with grain direction and weaknesses. They would orient the grain of a sledge runner to run lengthwise, following the direction of travel, to maximize its resistance to splitting. The constant application of water or animal fat lubricant served a dual purpose. It reduced friction, and it kept the wood from drying out and becoming brittle, maintaining its crucial flexibility throughout the long journey. Even the pathways themselves were engineered materials. Before a single log was laid, the ground was often prepared with a layer of crushed limestone or packed clay. This created a stable, uniform surface that would not turn to mud or deform under the localized pressure of the rollers. In some cases, archaeologists have found evidence of wooden trackways, like the famous Sweet Track in England, showing that building roads for heavy transport was a known practice millennia before the Romans. The tools used to shape these paths and quarry the stones were extensions of this material wisdom. While we picture copper chisels in Egypt, many cultures relied on even simpler, more profound methods. Stone hammers made from a harder rock like dolerite could be used to pound and fracture granite along desired lines. Wooden wedges swollen by water provided a slow, steady, and immense splitting force. The use of abrasive sand, dragged back and forth with a wooden saw, allowed for the precise cutting and shaping of surfaces. Each of these techniques worked with the properties of the material, using patience and repeated application of a manageable force to achieve what a single, powerful blow could not. This entire material ecosystem was defined by its limitations. A rope could only be so thick before it became unmanageable, which meant using multiple ropes in parallel. A wooden lever could only be so long before it would snap, dictating the size of the lifting team and the height of each incremental raise. These constraints forced a distributed approach to the problem. Instead of seeking one magical tool, ancient engineers used many small tools in perfect coordination, ensuring that no single point of failure could doom the entire endeavor. The successful transport of a megalith stands, therefore, as a monument to deep material intelligence, a proof that understanding the soul of a fiber, the heart of a tree, and the skin of the earth was the first and most essential step in moving a mountain. The ancient calendar was not just for planting crops, it was a blueprint for moving mountains. Master engineers understood that the environment was not a static stage, but a dynamic partner with its own powerful rhythms. Their greatest logistical triumphs came not from fighting these cycles, but from weaving their projects directly into the fabric of the seasons, turning predictable natural events into an invisible workforce. Think of the frozen north. In regions with harsh winters, the ground's transformation was a seasonal gift. What was soft, boggy earth in summer became a solid, frictionless highway of ice and packed snow. Hauling a multi-ton sledge across this frozen landscape required a fraction of the effort needed in warmer months. The cold ground could support immense weight without sinking, and the slick surface allowed sledges to glide with remarkable ease. This was not a hardship to endure, but a window of opportunity to exploit, scheduling the most grueling overland hauls for the time when nature itself lent a helping hand. In temperate climates, the rhythm shifted to the rains. The wet season turned clay-rich soils into a perfect, self-replenishing lubricant. Teams could prepare their earthen trackways and then simply wait for the skies to open. The rain would soften the ground to an ideal consistency, creating that crucial slippery layer between sledge runners and earth. This natural lubrication system was automatic, sustainable, and perfectly timed. It meant the most physically demanding work coincided with periods when the environment literally smoothed the path forward, a brilliant synchronization of human labor with the hydrological cycle. But the most profound partnership was with the rivers. In ancient Egypt, the entire logistics of pyramid construction were choreographed around the heartbeat of the Nile. The annual inundation was not a disruptive flood to be feared, but a vital phase of the construction timetable. Quarrying operations in Aswan would work through the drier months, extracting and shaping the granite blocks. Then, as the floodwaters began to rise, these finished stones would be loaded onto barges at riverside docks. The swelling Nile would lift the heavy vessels, allowing them to float freely, and its northward current would provide the propulsion for the long journey to Giza. The flood transformed the landscape, filling canals and channels that were dry for most of the year, creating a temporary network of waterways that reached right to the edge of the desert plateau. By the time the waters receded, the stones had arrived at the building site, ready for the next phase of work. This strategic scheduling was a form of genius. It conserved human energy on a colossal scale. Why fight the mud when you can use it? Why drag a stone across dry land when a river will carry it for you? This approach also protected their precious materials. Moving heavy sledges over dry, rough ground could quickly wear down wooden runners and fray ropes. Performing the same work on wet clay or ice drastically reduced this wear and tear, making the tools themselves last longer. This reveals a mindset of profound observation and patience. These projects were not rushed. They were paced over decades, even generations, allowing planners to think in terms of annual cycles, not just daily tasks. The environment was seen as a kit of tools that became available at different times: ice in winter, mud in spring, high water in summer. The master builder's skill lay in knowing the schedule of this natural toolkit and assembling the project in harmony with it. In the end, the movement of megaliths was as much about timing as it was about tension or traction. It was about listening to the world and choosing the moment when the earth itself was most willing to help. A stone's journey was never just about physics. The immense effort required to move a megalith only makes sense when we see it through the eyes of the people who moved it. For them, these were not inert blocks of rock, but vessels of meaning, charged with spiritual power and communal identity. The how of transport was inseparable from the profound why. Consider the blue stones of Stonehenge, hauled over 100 miles from the sacred Preseli Hills. Why choose such a distant source when local stone was available? To the builders, the stones themselves were likely seen as inherently powerful, perhaps imbued with the essence of their point of origin. Bringing them to Salisbury Plain was not a logistical headache, but a sacred pilgrimage, an act that physically connected their ceremonial center to a distant, holy landscape. The labor of transport transformed the stones into relics, their value multiplied by every mile traversed. The journey itself became a ritual, a prolonged ceremony where the collective effort of pulling ropes and chanting in rhythm reinforced social bonds and expressed devotion. In ancient Egypt, the pyramid was not merely a tomb, it was a machine for resurrection, a launchpad to the stars for the divine pharaoh. Every granite block floated down the Nile was a brick in this celestial vehicle. The act of construction was a national religious duty, a project that unified the kingdom in service to a god-king. Participation guaranteed a place in the cosmic order, turning back-breaking labor into an honor. Political motive was equally powerful. A ruler who could command the movement of mountains demonstrated a control over both nature and people that was nothing short of supernatural. It was the ultimate statement of authority, a permanent advertisement of a society's organizational power and the leader's divine mandate. Look at the Moai of Rapa Nui. These were not simple statues, but deified ancestors whose presence channeled protective energy, or mana, into the community. The process of carving, walking, and erecting a Moai activated this power. The statue's long, ceremonial walk from the quarry to the coast was likely a public spectacle, a tangible demonstration of a clan's strength and their ancestral connection. The effort expended was not a cost, but an investment in spiritual security and social prestige. This cultural lens changes everything. It means the slow, rhythmic pace of moving a stone with levers was not inefficient, it was intentional. It allowed for ceremony, for songs, for the entire community to witness and participate in the creation of their legacy. The path the stone took might have been a sacred processional way, its route predetermined by myth or astronomy. The final act of raising the stone was not just a technical feat, but a moment of profound spiritual alignment, locking the community's story into the very bones of the earth. When we view these projects through this dual lens of engineering and belief, the monuments cease to be silent ruins. They become the frozen echoes of songs sung by thousands, of shared purpose that turned impossible weight into a collective act of meaning. The stones did not move in spite of the belief, they moved because of it. Separated by vast oceans and thousands of years, ancient builders never met, yet they often spoke the same language of motion. A stone sledge pulled over a lubricated track in the Egyptian desert finds a startling echo in the lush highlands of Mesoamerica. While no wooden sledge has survived the humid climate there, the immense stone heads of the Olmec civilization, some weighing 20 tons, had to travel nearly 60 miles from their volcanic source. Without the wheel or draft animals, the most plausible method aligns perfectly with Egyptian practice: a massive wooden sledge on a prepared, slippery road. Similarly, the principle of the lever and pivot, used to raise the stones of Stonehenge, appears in detailed carvings from ancient Assyria and in historical accounts of construction in China. This is the phenomenon of convergent technological evolution, where isolated cultures, facing identical physical constraints, independently arrive at nearly identical solutions. The laws of physics are universal. Gravity, friction, and mechanical advantage work the same in the Nile Valley as they do in the Mexican jungle. When your only tools are wood, rope, and human labor, the menu of effective options for moving massive weight is surprisingly short. The sledge, the lever, the roller, and the ramp are not just ideas. They are the inevitable conclusions of a shared dialogue with material reality. This pattern of parallel invention strongly suggests that each culture, through trial, error, and observation, rediscovered these fundamental principles. They were not copying a blueprint from a lost global civilization, but reading from the same universal textbook written in stone and soil. The process likely began with simple observation, noticing that a round log rolls, that a long pole provides more lifting power, that wet mud is slick. From these basic truths, each society engineered its own sophisticated application, tailored to its specific environment and resources. The Egyptians used the Nile as their conveyor belt. The Rapa Nui Islanders used the statue's own form as a walking mechanism, and the builders in Britain may have used a combination of waterways and glacial valleys. The core physics remained constant, but the cultural expression of that physics was beautifully diverse. Yet, this global tapestry also holds threads that hint at something more: the subtle diffusion of ideas along ancient trade routes. While a sledge is an obvious invention, some specific techniques show a curious specificity. The use of a counterweight basket in a wooden frame for lifting, for instance, appears in multiple regions across Eurasia over centuries. Could this particular configuration have traveled along the Silk Road, passed from one master builder to another? It is possible that while the broad principles were independently discovered, the refined tricks of the trade, the clever knots, the ideal wood choices, or the precise ramp angles were shared commodities of knowledge among the elite craftsmen of the ancient world. Whether through independent spark or slow cultural exchange, the result is a powerful testament to a shared human genius. When confronted with a mountain of a problem, minds across the globe lit up with similar sparks, proving that ingenuity is not the property of any one culture, but a fundamental trait of our species. This convergence makes the silent stones speak a common story, one of curiosity, perseverance, and the universal urge to leave a mark that defies time itself. The allure of a single, lost secret is powerful. It is tempting to believe that the movement of these stones relied on a technology so advanced we have forgotten it entirely, or perhaps on guidance from sources beyond our world. These ideas fill books and documentaries, proposing everything from sonic levitation using ancient chants to the manipulation of gravity with crystals or forgotten energy fields. Some point to the precise astronomical alignments of these sites as evidence of knowledge that seems to surpass the era, or to myths from various cultures that speak of gods or giants assisting in construction. These narratives are compelling because they offer a kind of magic, a clean and wondrous key that unlocks every mystery at once. They transform our ancestors from ingenious engineers into custodians of a power they did not fully understand, which can feel more satisfying than the slow, gritty reality of ropes, levers, and mud. Yet, when we subject these theories to the same scrutiny we apply to the archaeological record, they begin to unravel. The central issue is one of evidence, or rather, the consistent lack of it. Not a single tool, inscription, or material trace has ever been found that points to a device for anti-gravity or acoustic levitation. The stones themselves show clear marks of quarrying with stone hammers and wooden wedges, not precision cuts from high-tech tools. The transport paths reveal grooves from sledges and post holes for leverage, not the smooth, unmarked ground one might expect from floating stones. This absence is profound. If such revolutionary technology existed and was used on such a scale, its material footprint would be everywhere in the archaeological layers, just as we find countless examples of simple tools, pottery shards, and construction debris. Furthermore, the proposed methods often fail a basic physics test. The energy required to levitate a 50-ton block of granite through sound waves, for instance, is staggering and would likely shatter the stone before it lifted it an inch. These speculative theories also do something subtle. They can inadvertently diminish the genuine achievement. To suggest that humans needed outside help or lost super science to build these wonders is to underestimate the extraordinary power of cumulative knowledge, observation, and coordinated labor. It overlooks the 200 years of progressive engineering development visible in the pyramid building sequence itself, from the stepped pyramid of Djoser to the smooth-sided perfection of Giza. It ignores the experimental archaeology that has successfully moved megaliths with nothing but human strength and Neolithic tools. The persistence of these ideas tells us more about our modern mindset than about the ancient past. In a world of instant technological solutions, the patient, generational work of thousands can feel alien, almost unbelievable. A magical explanation is simpler, more cinematic. It places the wonder outside of us in a realm of mystery rather than within us in the realm of persistent collective effort. The growing body of evidence, however, points unambiguously toward the latter. Every new discovery, from the harbor complex at Giza to the quarry roads at Baalbek, reinforces a picture of sophisticated, entirely human engineering. This reality is, in its own way, more astonishing than any fiction. It means that the greatest technology our ancestors possessed was not a device, but an idea, the ability to organize, to plan across generations, and to harness the fundamental laws of the physical world with nothing but creativity and will. That is a secret worth remembering, and it is one we have not lost. The principles that raised pyramids and walked statues were not sealed away in a tomb. They flowed like a river through time, irrigating the minds of later builders and shaping the physical world we inhabit today. This knowledge of mass, force, and collective effort became a silent inheritance passed down through the very act of building. The Romans, masters of empire and infrastructure, stand as direct heirs to this legacy. While they employed more advanced tools like iron and the pulley, their foundational approach to moving colossal weight was strikingly familiar. To transport the 50-ton granite columns for the Pantheon's portico from Egyptian quarries to Rome, they did not reinvent the wheel. They used the ancient, proven method of massive barges on the Mediterranean, navigating the stone across the sea before likely transferring them to sledges on lubricated ramps for the final inland journey. Their innovation was one of scale and documentation, creating a standardized, repeatable process that could be deployed across an empire. The organizational blueprint for managing tens of thousands of workers on projects like aqueducts and amphitheaters can be traced back to the social engines that mobilized labor for the pyramids, proving that the true breakthrough was often administrative as much as it was physical. Centuries later, in the shadow of emerging Gothic cathedrals, the echo of megalithic thinking resonated in stone once more. The challenge of raising skyward spires and setting massive carved saints into high niches demanded the same intimate understanding of leverage and counterweight. Medieval master masons, though armed with more sophisticated mathematics and crane technology, still relied on the fundamental physics of the frame and the inclined plane. The construction of a cathedral was a generational endeavor, a community-wide project that mirrored the cyclical, seasonal labor of ancient times. The precise fitting of immense stained glass windows into stone tracery required the same patient, incremental adjustment as seating a Stonehenge lintel, a testament to a problem-solving lineage that never truly broke. This thread continues unbroken into our modern age. The principles of distributing load, managing ground pressure, and coordinating vast teams are the bedrock of civil engineering. When we watch a modern crane slowly rotate a prefabricated bridge section into place, we are seeing the direct descendant of the lever and pivot technique, now powered by hydraulics instead of human muscle. The logistical software that schedules deliveries for a skyscraper's construction is a digital evolution of the ancient administrator's clay tablet, tracking the movement of stones down the Nile. So these ancient endeavors were not curious dead ends but vital, foundational chapters. They were humanity's first graduate studies in the laws of physics and the art of collaboration. Each successful movement of a megalith was a data point, an experiment that proved what was possible when will and wisdom were combined. This accumulated knowledge, this deep material intelligence, became part of our cultural toolkit. It taught us to see the environment not just as a source of materials, but as a partner in construction, to read the seasons as a construction schedule, and to understand that the greatest forces can be mastered through the clever application of small, repeated actions. The legacy is all around us, not just in the surviving stones, but in every modern structure that stands against gravity. It reminds us that our current technological world was not born in a vacuum, but was built layer upon layer, idea upon idea, on the strong, ancient foundations laid by those first engineers who looked at a mountain and decided to make it walk. That dialogue between past and present is not confined to academic journals. It has stepped out into the sunlight, becoming a public spectacle of sweat, strain, and shared discovery. Across the globe, teams of researchers, students, and enthusiasts are taking these theories off the page and putting them to the ultimate test, attempting to move massive stones using only the tools and methods of antiquity. These modern reconstructions are more than experiments. They are living history, transforming abstract concepts into a visceral, physical experience. In Japan, the legacy of moving massive stones for castle construction is celebrated and actively preserved. At festivals and cultural demonstrations, groups dressed in traditional attire perform what is known as the Nabore-ishi technique. They work in coordinated teams to move multi-ton stone blocks up steep slopes using nothing but wooden levers, ropes, and a system of log rollers. The rhythmic chanting and synchronized movements are not just for show, they are a functional necessity, a precise choreography that demonstrates how sound and motion could unite a team to achieve the seemingly impossible. Watching a 2-ton slab inch its way up an incline, powered solely by human rhythm, makes the scale of ancient projects suddenly, breathtakingly real. Similarly, documentary filmmakers and university departments have taken on the challenge of replicating specific ancient techniques. One notable project involved a team attempting to move a 1-ton replica of an Egyptian pyramid stone using a sledge on a lubricated track of wet clay. The process was deceptively simple in theory but grueling in practice. teams quickly learned the critical importance of the lubricant's consistency. Too dry and the sledge stuck fast, too wet and it became uncontrollable. They discovered the exact rhythm needed for the pullers, a steady, unified heave rather than a series of frantic jerks. These hands-on trials often reveal the hidden nuances that ancient texts never mention, the way a rope must be tied to distribute force evenly, or how a slight incline changes everything. Each stumble and adjustment in these modern attempts deepens our respect for the original engineers, who perfected these methods through generations of trial and error. These public demonstrations serve a powerful dual purpose. For the audience, they are an unparalleled educational tool. It is one thing to hear that a stone weighs 50 tons. It is another to stand beside a 1-ton block and watch 10 people struggle to budget an inch. That tangible scale creates a direct, emotional connection to the past, fostering a deeper appreciation for the ingenuity and effort involved. For the researchers, these events are active laboratories. Every successful lift or controlled slide generates valuable data on force, friction, and human endurance, refining our models of how these projects were planned and executed. They prove that the conversation with our ancestors is not over. We are still asking them questions, and through the language of physics and effort, they are still offering us answers. The stones may be silent, but in these modern acts of recreation, their story finds a new voice. The story is not over. For every mystery we solve, another seems to emerge from the soil, reminding us that the past holds its secrets close. The field of megalithic studies is far from static. It is a living, breathing detective story where each answer reveals a deeper layer of questions waiting to be asked. Take the monumental stone circles of Göbekli Tepe in Turkey, a site that rewrote history by predating Stonehenge by thousands of years. Here, immense T-shaped pillars, some weighing over 10 tons, were erected by a society we once thought incapable of such feats. Yet, the exact paths these stones traveled from nearby quarries remain elusive. Archaeologists scour the landscape, not with shovels alone, but with eyes in the sky. LiDAR technology, which uses laser pulses to map the ground beneath forest canopies, is revealing subtle traces, ancient trackways and quarries invisible to the naked eye. This high-tech tool is like giving the land an X-ray, exposing the ghostly footprints of prehistoric engineering that have slept for millennia. Similarly, at Stonehenge, the focus has shifted from the famous Sarsen circle to the smaller bluestones. While we understand their distant Welsh origin, the exact route, whether entirely overland or using a combination of rivers and coastal waters, is still hotly debated. Researchers now employ microscopic analysis of soil samples taken from the stones themselves, searching for pollen grains or mineral signatures that could pinpoint the specific environments the stones passed through on their long journey. It is forensic science applied to archaeology, reading the stone's biography in particles smaller than a grain of sand. Even the grand trilithons, the iconic 3 stone structures of Stonehenge, pose a fresh puzzle. Recent excavations suggest the giant Sarsens may have been dragged along a route that purposely avoided the easiest path, perhaps for ceremonial reasons. This introduces a fascinating new variable. The journey may not have been about efficiency, but about ritual. Computer modeling allows researchers to simulate these different routes, calculating the energy expenditure and manpower required for each, testing theories in a digital landscape before a single volunteer lifts a rope. This dynamic interplay between old and new methods ensures the mystery never grows stale. A discovery in a quarry can append decades of theory. A new scan of a familiar field can reveal a hidden road. The public plays a role too, as citizen scientists and dedicated enthusiasts often bring fresh perspectives or notice details that change the conversation. This ongoing research does more than satisfy curiosity. It refines our understanding of human capability. It shows us that ancient people were not just moving stones, they were making deliberate, meaningful choices, embedding their worldview into the very act of transport. The frontier of this knowledge keeps expanding, proving that the final chapter on these ancient giants has yet to be written. The stones are silent, but the communities connected to them are not. Our fascination with ancient engineering carries a profound responsibility, one that extends beyond the physics of levers and ropes to the ethics of memory and respect. These monuments are far more than scientific specimens in an open-air museum. They are living chapters in the ongoing story of a people. The moment we shift from asking how a stone was moved to considering why it matters, we enter the vital realm of cultural heritage, where knowledge must be paired with sensitivity. This is especially clear on Rapa Nui, where the Moai are not relics of a vanished culture, but direct ancestors to the island's present-day community. For decades, archaeological work proceeded with the stones as the primary focus, often overlooking the insights and spiritual connection of the Rapa Nui people themselves. Today, a new paradigm is taking hold, one built on collaboration. Researchers now work alongside community elders and cultural practitioners, blending scientific methods with traditional knowledge passed down through generations. This partnership enriches the investigation, as oral histories about the statues walking are no longer dismissed as myth, but valued as crucial clues that led to the successful walking experiment. It transforms archaeology from an extraction of data into a shared conversation, ensuring that the story told is complete and honors those for whom the stones hold deepest meaning. This collaborative model is a guiding light for work at sites worldwide. It acknowledges that the descendants of the builders are the rightful stewards of their own history. The challenge of preservation in the face of modern tourism brings this tension into sharp focus. Millions of visitors each year bring economic opportunity, but also the slow, steady wear of countless footsteps, the corrosive effects of humidity from human breath in enclosed tombs, and the risk of accidental damage. Balancing public access with protection is a constant negotiation. At Stonehenge, the solution was to move the visitor center away from the stones and keep people at a respectful distance on a designated path, preserving the site's dignity while allowing everyone to experience its power. In Egypt, strict limits on the number of people inside the Great Pyramid at any one time help protect its ancient surfaces. These measures are not about keeping people out, but about ensuring these wonders survive for centuries to come. They require us as modern visitors to see ourselves not just as spectators, but as temporary guardians. The ethical path forward is one of partnership and perspective. It means listening as much as we measure, protecting as fervently as we promote, and remembering that our quest to understand the how is ultimately in service of honoring the who. The true legacy of these stones is not locked in their mineral composition, but in the living culture they continue to represent and inspire. That sense of awe is not a modern accident. It is the intended echo of an ancient feeling, a psychological resonance built stone by stone. To stand before a completed pyramid or within a circle of towering megaliths is to feel a shift in perspective. You are confronted with an object that defies your personal scale, something that took generations to conceive and build. This triggers a profound emotional response, a blend of wonder at the achievement, humility before its endurance, and a spark of inspiration about what people can do together. This awe is not just a spectator's reaction, it was likely the very fuel that powered the projects from the beginning. For the ancient builders, the psychological impact was immediate and transformative. After years or decades of labor, seeing that final capstone set or that last statue raised would have generated an overwhelming collective pride. It was a tangible proof of their society's strength, coordination, and divine favor. This was not just a building, it was the physical manifestation of their shared identity and purpose, solidifying social bonds and creating a legacy that literally anchored their community to the land. The monument became a story written in granite, a story they were all authors of, teaching future generations about their capability and their place in the world. For us, separated by millennia, these structures serve a different but equally vital purpose. They are permanent counterarguments to the idea of linear progress or primitive incapability. They challenge the subtle assumption that ancient people were less intelligent, less creative, or less ambitious than we are. Their achievements whisper a powerful truth. Human potential is not defined by the tools in our hands, but by the vision in our minds and the unity in our communities. They remind us that resilience is not just about enduring hardship, but about channeling effort toward a horizon far beyond a single lifetime. When we look at these stones, we are not looking at a mystery to be solved so much as a mirror held up to our own capacity. They ask us what we could achieve if we were united by a common, generational vision. They prove that creativity flourishes within constraints, that the most sophisticated solutions are often elegantly simple, and that the true engine of history is not technology alone, but the human will to collaborate on something greater than oneself. In a world often focused on the individual and the immediate, these ancient sites pull our gaze upward and outward. They reconnect us with a deeper timeline where patience was a virtue and legacy was a collective project. That lingering feeling of awe is more than just admiration. It is an invitation to remember what we are capable of when we choose to build together. A single archaeologist with a trowel cannot unlock this mystery alone. The true picture only emerges when different fields of study converge, each bringing its own unique lens to the same set of stones. This is the power of interdisciplinary research, a modern echo of the ancient collaboration it seeks to understand. Geologists act as the first detectives, using the stone's own chemical fingerprint to pinpoint its origin. By analyzing the microscopic crystals and trace minerals within a bluestone from Stonehenge or a granite block from a pyramid, they can match it to the exact quarry outcrop, sometimes hundreds of miles away. This is not just about location, it defines the entire scope of the journey, giving us the starting point of the epic. Once the route is known, physicists and engineers step in. They calculate the coefficient of friction on wet clay, model the stress on a wooden sledge under 80 tons of load, and determine the exact mechanical advantage of a 10-meter-long lever. Their equations transform speculation into testable models, showing us precisely how many people would be needed to pull a given weight up a 5-degree slope, or how much counterweight would be required to lift a lintel. They turn the art of construction into a reproducible science, but the numbers only tell part of the story. This is where anthropologists and ethnographers provide the crucial human context. They study the social structures of traditional societies, examining how labor is organized, how knowledge is passed down, and how collective projects reinforce community bonds. Their work helps us envision the society that could sustain such an effort, moving beyond the mechanics of the how to explore the profound cultural why. Even botanists have a vital role, identifying ancient pollen grains trapped in the soil of a transport route, or analyzing the fibers in a fragment of recovered rope to understand the materials available. This collaborative model reveals a fundamental truth. The ancient builders themselves were interdisciplinary thinkers. They were geologists selecting the right stone, physicists intuiting leverage, engineers designing ramps, and leaders organizing labor. To understand them, we must emulate their holistic approach. The future of unraveling these mysteries lies not in isolated specialties, but in this synthesis of knowledge where a chemical analysis, a physics equation, and an anthropological insight finally combine to make the stones speak with one clear, collective voice. The journey of a single stone is a story about the journey of our entire species. These massive undertakings are not isolated curiosities. They are the foundational chapters in the story of human civilization. Before the written word, before empires, even before the wheel in many places, Our ancestors were already mastering the arts of large-scale project management. They were learning to plan not for a season, but for a generation, to marshal resources across vast distances, and to solve problems of physics with nothing but observation and ingenuity. The movement of a megalith was, in essence, humanity's first major venture into civil engineering. It required a vision so grand it could only be fulfilled by a society that had learned to work as one. This marks a profound shift in our relationship with the world. For millennia, humans adapted to their environment, following herds, gathering plants, living within the rhythms of nature. But with these projects, something new emerged, a deliberate, permanent act of reshaping. It was the decision to take a piece of a distant mountain and place it exactly here, to align a circle of stones with the solstice sun, to build a mountain of your own pointing to the stars. This was not adaptation, it was assertion. It was the moment we began to write our intentions directly onto the landscape, using stone as our pen. In doing so, we invented new forms of social organization. You cannot feed, house, and coordinate 1,000 people for a decade without developing systems, hierarchies, and specialized roles. The project manager, the surveyor, the master rope maker, the quartermaster, these professions were born from the necessity of moving mountains. This social engine was as much an innovation as the lever or the sledge. It proved that we could achieve objectives far beyond the capacity of any individual or family, that we could pool our labor, our knowledge, and our will toward a common horizon. This collaborative capacity is arguably the bedrock of every complex society that followed. Furthermore, these endeavors represent the birth of applied physics as a practical craft. Long before it was a formal science, the principles of mechanical advantage, friction, and buoyancy were being tested, refined, and passed down through hands-on experience. The ancient engineer knew that a longer lever made lifting easier, that wet clay reduced drag, that a round log rolled. This was knowledge earned through trial and error, through careful observation of the material world, and it formed a technical legacy that would be built upon for thousands of years. So when we stand before these ancient stones, we are not just looking at a monument, we are looking at the birthplace of ambition itself. We are witnessing the point where abstract ideas, community spirit, and raw effort fused into a tangible, enduring form. They teach us that civilization is not defined by cities or writing alone, but by the shared capacity to imagine a future and then to labor together across generations to bring it into being. The true legacy of these megaliths is not the rock itself, but the indelible proof they offer that when humanity unites behind a vision, even the earth itself can be persuaded to move. From the sledges of Egypt to the walking Moai of Easter Island, this story is not one of magic but of method. It is a testament to human ingenuity in the face of daunting natural challenges. We have journeyed together through the physics of friction and leverage, the social engines of coordinated labor, and the profound beliefs that transformed backbreaking work into sacred purpose. These ancient civilizations turned the impossible into reality through a blend of deep observation, patient organization, and sheer determination. They did not possess a secret technology we have lost. They possessed something more powerful, a shared vision, and the collective will to see it through across generations. The stones they moved are far more than silent monuments. They are active messages from the past. They speak to us of a capacity for collaboration that is fundamental to our species, a reminder that our greatest achievements are not the work of isolated genius, but of communities united by a common goal. They stand as eternal proof that when we align our efforts, we can reshape the very world around us. So let this exploration linger with you. Let it spark your own curiosity. What are the seemingly impossible challenges we face today, and how might we overcome them with a similar unity of purpose and creativity? The lessons are written in stone, waiting for us to read them anew. Share your thoughts in the comments below, and subscribe to continue unraveling history's greatest puzzles.